All right, so here's what we got so far. We have the power rule, that the derivative of x to the n is equal to n times x to the n minus 1. There's a couple special cases here that you should be aware of. The derivative of x is just 1. The derivative of a constant times x is just the constant times 1, which is the constant. And the derivative of a constant all by itself is just 0. And the way I would really, really encourage you to think of these particular special cases are just slopes of lines. The line y equals x has a slope of 1. Its derivative is 1. The line y equals c times x, or y equals m times x, has a slope of m. Its derivative is m. Or the line, sorry, I said cx. The line y equals c times x has a slope that is c. Its derivative is c. The line y equals c, which is a horizontal line, has a slope of 0, and its derivative is 0. So even though you can remember these in other ways, I think it's nice to think about, oh, for these straight lines, x, constant times x, and horizontal line, their derivatives are always just their slopes, since their slopes are the same everywhere on the line. And then, of course, we have a couple other derivatives we talked about. We've talked about how the derivative of e to the x is e to the x. And we've talked about how the derivative of, I think I showed you guys last time, how the derivative of sine of x is equal to cosine of x. And I'm pretty sure I also said the derivative of cosine of x is equal to negative sine of x. And that's, as far as I know, that's the things we've talked about in this class, kind of at least derivative rules summed up very quickly here. So let's erase some stuff. So let's drop the eraser, you know. Ah, man, all this black dust is just gross. Oh well. Can't do anything about it. So, oh, and then of course I should say, we do have the product rule. The fast way of writing it being that, you know, the derivative of f times g is f prime g plus f g prime. Or f of x times g prime of x plus f of x, f prime of x times g of x. Okay. But I do think it's worth your while to see how the product rule is proven. And it's not hard to do. So I want to prove the product rule. So I'm going to find the derivative of f of x times g of x. And of course, well, maybe not of course, a lot of the time, when we were trying to find the derivative of a new thing, we go back to the limit definition of the derivative. So I know that if I call this for a second capital F of x, then the derivative of capital F of x is the limit as h goes to 0 of capital F of x plus h minus capital F of x all over h. The reason we do this capital F of x thing is because some people are like, well, it's weird to say that this function of x plus h is little f of x plus h times little g of x plus h. But that's really what it is. And we use this capital F to just kind of make it more clear. Oh yeah, if capital F of x is little f of x times g of x, then capital F of x plus h is little f of x plus h times g of x plus h. So it's, to me, it feels like a slightly unnecessary step, but it's fine. So it's the limit as h goes to 0 of little f of x plus h times g of x plus h minus capital F, which is just little f of x times g of x over h. I think my blue pen is starting to go. So then what we do something tricky. We do something because we know what we want the answer to be. We're going to write this as, I think I have enough. Oh, let me see. So this is going to be the limit as h goes to 0 of same thing. So then I'm going to subtract something and add something in. So I'm going to subtract a thing, I'm going to add a thing, and I'm still going to have minus f of x times g of x. And the thing I'm going to subtract and add is the following. It's f of x times g of x plus h and f of x times g of x plus h, right? We're totally allowed to add and subtract the same thing. I haven't changed anything at all. I've just changed how it looks. But now we're going to break this up into two very specific fractions. I'm going to break it up into the first two pieces over h plus the second two pieces over h. And I'm going to write it all in red because my blue pen is starting to die. This is going to be the limit as h goes to 0 of this minus this over h. So f of x plus h, g of x plus h, minus f of x times g of x plus h, all over h, plus f of x times g of x plus h, minus f of x times g of x, all over h. All right, so now the important thing to observe. From this first piece, what can I factor out from the top? And I know you might not be able to see this very well. F of x plus h times g of x plus h minus f of x times g of x plus h. So I can factor out the thing that's the same, which is g of x plus h. And yeah, I'm going to erase up here because I've got some room. I don't really need this anymore. So this is going to equal the limit as h goes to 0 of, I'm going to write this out as, so I'm going to factor out the g of x plus h. So I'm going to write this as f of x plus h minus f of x all over h times g of x plus h. Plus, same idea here. Here I have f of x times g of x plus h minus f of x times g of x. I'm going to factor out the thing that's the same, which is f of x. So f of x times the remaining fraction is g of x plus h minus g of x all over h. Okay, and now we've got this right where we want it. I'm going to ask you guys some questions here. What's the limit as h goes to 0 of f of x plus h minus f of x all over h? There's a name for that limit. It's the limit definition of the derivative of f. That's why we wrote it that way. Okay, this is not nearly as exciting. As h goes to 0, what's the limit as h goes to 0 of g of x plus h? Well, then you just let h go to 0, and you get g of x plus 0, which is g of x. Plus, the limit as h goes to 0 of f of x is just f of x. There's no h's in there to mess things up. And then every one of you should at least be able to say to yourselves, I almost colored my face with my pens here, internally, what's the limit as h goes to 0 of g of x plus h minus g of x all over h? Oh, that's the limit definition of the derivative of g. Right, g prime of x is literally defined to be the limit as h goes to 0 of g of x plus h minus g of x all over h. And look, we have the product rule. F prime times g plus f times g prime. So there you have it. The product rule is what it is. It works. You definitely should memorize the product rule, like without a doubt. And yeah, so questions about this before we do a couple more examples. Okay.
Oh, real quick. When you multiplied, or when you added f of x times x plus h plus f of x, sorry, the middle portion, the red, yeah?
Yeah, the minus f of x times g of x plus h plus f of x times g of x plus h.
Yeah, that's the same thing of adding 0 to the function, right?
Exactly, right? If you add and subtract the same thing, you're just adding 0 to the expression.
Great, thank you.
Totally legal.
Yeah.
You can always add 0. You can always multiply by 1. So then, just as a quick reminder, we can use the product rule to take the derivative of something like x to the 6th times e to the x, which is going to be the derivative of the first part, 6x to the 5th, times the second part left alone. I know that's also the derivative of the x, but I'm not differentiating e to the x there. I'm just leaving it as e to the x, plus the first part, x to the 6th, times the derivative of e to the x, which is e to the x. That's the derivative of x to the 6th times e to the x. In a similar way, we could say that the derivative of, I don't know, x to the, let's say 5x to the 7th times cosine of x. So with that 5, you can either leave it out in front as a constant, but I personally like to kind of group it with the x to the 7th. So I'm thinking of like this as one of the things multiplied together, and this is the other piece. So I'm kind of thinking of this is my f and this is my g. So my derivative here is f prime, which is going to be 35x to the 6th times the g, right? So this is f, this is g. There's f prime times g. Or as I like to say, the derivative of the first thing, leave the second thing alone, plus then switch it. Leave the first thing alone, take the derivative of the second thing. Derivative of cosine is negative sine of x. And in this case, I definitely would rewrite it as this minus, that with the minus sign there. So I would definitely, like the cheater way to do it is be like, I'm going to subtract, I'm going to erase that and change that. Right, that's how I would actually write my answer because it's better that way. Although sometimes, especially on an exam, sometimes it'll be like, find the derivative, you don't have to simplify. You could just leave it like that. But if you, even then, you should simplify it. So those are a couple examples of the product rule. Let's talk about the quotient rule, which the quotient rule and the product rule are really, really very similar.
It doesn't matter what order you derive first. If you derive like
the product rule, it does not. Exactly. So actually, that's a good point. You could totally also do this as the derivative of that times that left alone plus the derivative of that, which is 35x to the 6th, times that left alone. Same thing. And the reason it's the same is because it doesn't matter what order you multiply things in or add things in. You still get the same result. 2 plus 5 is equal to 5 plus 2. 2 times 7 is equal to 7 times 2. They are what are called commutative operations, meaning the order that we do them in doesn't matter. But I will caution you very strongly that is not true for subtraction or division. So while order doesn't matter for the product rule because you're only using the operations of addition and multiplication, it certainly matters for the quotient rule where you're using subtraction and division. And that's part of the reason we write the product rule the way we do, so that it kind of matches up with the same order as the quotient rule. So while just to even say further, so while you can definitely do it either way, I would recommend thinking of it as the derivative of the first thing times the second thing left alone, and then flip it so that you have it in the same order that you're going to see things in for the quotient rule, like we're going to do right now. So, let me write the product rule again, because we're going to see how it kind of matches up with the quotient rule. So the product rule says the derivative of f times g is f prime g plus f g prime. You can write it out more lengthily, like f of x times g of x is f prime of x times g of x plus f of x. But the of x part is very much implied here. So that's the product rule. The quotient rule, we're taking the derivative of a quotient, is the derivative of f divided by g. I mean, you could do g divided by f, but it's very standard to write it as f divided by g. And so I'm going to write out the formula, and I'm going to tell you what I say in my head. So the formula looks exactly like the product rule written in this order, except with subtraction instead of addition. So it's f prime g minus fg prime. So literally, right, it looks the same as the product rule, except we have a subtraction there instead of addition, divided by the denominator function squared. There's your quotient rule. Now, here's the way I usually say it when I'm saying it in my head. I say, okay, the derivative of f divided by g is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's just the way I say it. I don't know why I say it that way. That's just what works in my brain. So I'm thinking of this as, I'm really kind of thinking of it as g times f prime minus f times g prime all over g squared. Right? Because again, order of multiplication doesn't matter. Order of subtraction definitely matters. So I'm thinking of this as the bottom times the derivative of the top minus not enough room, fine, right over here. I'm thinking of this as the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's the way I say it in my brain. You can do whatever you want as long as it works. So a lot of people use the there's a mnemonic device. Some people sing it. I've never sang it, so I don't know the tune that this goes to. But the thing people also like to say is low D high minus high D low over low squared. Where low is the bottom, D high is the derivative of the top, minus high is the top, times D low is the derivative of the bottom, all over the low squared of the bottom squared. Or if you've got something else that works for you, use that. Just remember, it is vital that you get the order of subtraction correct. It has to be the bottom times the derivative of the top first, minus the top left alone times the derivative of the bottom. That's interesting. I think of it as like cross multiplication, starting with the derivative of the top. Okay, yeah. So like I said, whatever works for you, right? As long as it works for you, it works. Just make sure you're careful. I will also point out, right, if you're ever unsure, you have lots of tools at your fingertips. The Wolfram Alpha differentiator and also next order, the Wolfram Alpha integrator are definitely useful things to check work with. That said, you should be able to do these things on your own without help. So let's talk about some things. So I want to find the derivative of, sure. Well, I'm going to start off with something that maybe we kind of talked about last time. So 4x cubed times 8 root x plus 3 over 2x. What I want to say here is, yeah, I could use the quotient rule if I like pain, but I don't like pain. I don't want to suffer needlessly. So yes, you should definitely use the quotient rule when we need to. Here we don't need to, because we can divide each thing by 2x. I know we did an example like this either last class or the class before, but I can definitely write this as the derivative of 4x cubed over 2x minus 8 root x over 2x. I should probably write that as 8 times x to the 1/2 plus 3 over 2x, or 3 over 2 times x to the minus 1. I guess I can do that in the next step. So I'm going to simplify this a little bit more. I'm going to write this as the derivative of 4 over 2 is 2. X cubed over x to the first is x to the second. 8 over 2 is 4. X to the 1/2 over x to the first is x to the minus 1/2. And 3 over 2x is 3 over 2 times x to the negative 1. And then I've just written everything as powers of x, so I can just use the power rule. I'm going to get 4x. Let's see, minus 4 times minus 1/2 is plus 2. X to the minus 1/2 minus 1 is minus 3/2. And then I'm going to derivative this, the minus 1 comes down, so I get minus 3/2 times x to the minus 1 is minus 2. So typically, if something can be easily simplified like this, I often will avoid using the quotient rule. The same thing also applies even if you don't have just powers of x. For example, although it's a little less true, if I had something like, I want to take the derivative of, I don't know, cosine of x divided by x cubed. You could definitely use the quotient rule. In fact, we probably will in a second. But you could also rewrite this as the derivative of x to the negative third times cosine of x. So if my numerator was more complicated, like if I had multiple terms in the numerator, I probably wouldn't do this. But why is it 4x cubed over 2x instead of 4x squared over 2x? Because I might have made a mistake. So it's 4x cubed. So I think what is the issue here for the person that wrote me is that that's a 3 there, but it might look like a 2 to you. So that's why it's a 4x cubed, because I actually wrote a 3. I just wrote it very sloppily. So right, that was a 3, but the bottom of the 3 was a little wonky. So hopefully that clarifies your question. So here you can totally use the product rule and say, oh yeah, I've got the derivative of the first thing, so negative 3x to the negative fourth times cosine x plus x to the negative third times the derivative of cosine, which is negative sine. I will say, if you're going to write x to the negative third times negative sine, you should probably put some parentheses around it. Otherwise, it's going to look like you have x to the negative third minus sine of x. I would simplify this. I would write this as negative 3x to the negative fourth cosine of x minus x to the negative third sine of x. But yeah, like I was saying, if my numerator was more complicated, like if it was x to the fourth plus cosine x all over x cubed, even though you could break that up into multiple pieces and then simplify it, I probably wouldn't. There's only so much. But we could also use the quotient rule here. We use the quotient rule. Well, again, it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all of the bottom squared. Yes, I know a lot of you would prefer that I wrote negative sine x first times x cubed second. You can do it that way. I don't say it that way in my head, so that's not the way I do it. But you can totally say, oh, it's f prime, which is the derivative of cosine, times g, which is x cubed, and so on and so on. I probably wouldn't, so again, simplification is kind of can be a thorny subject. It depends on what your teacher wants, right? Sometimes they want you to simplify stuff, sometimes they don't really care. If they're just asking you to take derivatives, often they don't care. But I will simplify this one just to show you that they're actually the same. So if I was going to simplify this, I would do a couple things. I would first rewrite this as negative x cubed sine of x. I'm going to throw away this pen because it's trash, or miss the garbage can completely. Minus, it's usually standard practice to write powers of x before trig functions. So I would write this as 3x squared times cosine of x over x cubed squared is x to the sixth. Now I know those don't look the same yet. Typically what we do if we're simplifying a quotient rule is, yeah, Sarah, we definitely, whenever we're thinking of doing a quotient rule, we're always thinking of the numerator as the f and the denominator as the g. That is always what we're doing. Here, I would factor out whatever I could from the top. And that is a typical move when you're trying to simplify a quotient rule derivative. I'm going to factor out, let's see, I have an x cubed and an x squared, so I can factor out an x squared. If I factor out an x squared, I'm left with a negative x times sine of x minus 3 times cosine of x, all over x to the sixth. And then I can cancel an x squared there and an x squared there. So I'm left with negative x sine of x minus 3 cosine of x all over x to the fourth. And if I was doing a quotient rule, that's how I leave it, because that's considered pretty simplified. But if you want to see that these are the same, you could divide each thing by x to the fourth and say, oh yeah, -3 cosine x divided by x to the fourth is the same as -3 times x to the -4th times cosine x. And -x times sine of x divided by x to the fourth is the same as -x to the -3rd times sine of x. Because x divided by x to the fourth is x to the -3rd. And 3 divided by x to the fourth is 3 times x to the -4th. So they are the same. And typically people won't really care which way you answer this.
Wouldn't the order matter since you're doing g of x times the derivative of f of x?
Yeah, the order.
Oh, you just switched it.
So I'm not sure what order you're specifically referring to.
Oh, in the first part when you did x cubed times negative sine of x. Oh, I see. You just switched it because I thought you were doing g of x times f of x when it should be f of x times g of x.
So what I think you're missing a prime somewhere.
Mm-hmm.
So right, so yes, so you're right. I do my quotient rule slightly out of the regular order, and that instead of doing it as f prime g minus f g prime all over g squared, I often write it as g f prime minus f g prime all over g squared, because that's the way the words come out of my mouth. Right? I think of it as the bottom times the derivative of the top instead of the derivative of the top times the bottom.
Okay, yeah, I was just a bit confused.
No, yeah, and please let me know if there's anything I'm doing that is confusing, because I can fix my way of doing it to be more like what you guys want. But I really will stress, it's okay to multiply things in the opposite order, right? X cubed times negative sine, or negative sine times x cubed, same thing. And I will point out, regardless, let's pretend for a second that I had done it the other way. That I said, oh, I'm going to do it as f prime g, which is negative sine of x times x cubed. After that step, I still would have written it this way, because it's still very much the standard way to write the powers of x before we write the trig functions. So, but yeah, you're right. I sometimes do it slightly differently than you might be thinking of it. I will re-emphasize, whatever works for you works for you. But yes, please do. If you see something that you're not sure about, you're like, why is he doing it that way? Please let me know, because I will certainly explain it or fix it. Also, sometimes I make mistakes, right? So if I make a mistake, definitely say something. Okay, let's do some more quotient rule, because while these examples are fine, they're not really getting at the heart of the quotient rule, which is that sometimes you just have some complicated stuff. Like sometimes you might have a function that's like, I don't know. I guess I'm going to call it f because that's pretty usual. F of x is, which is one of the reasons why I say top and bottom instead of f and g. Let's say it's x to the fourth plus cosine of x over e to the x plus 2 sine of x. And although there are ways you could avoid using the quotient rule if you really, really, really wanted to, I wouldn't here. I would definitely use the quotient rule, even though you could avoid it if you so decided, if you know the chain rule. You have to know the chain rule, though, to avoid the quotient rule. So I don't really want to call this f because I've already used f. So that's why I'm going to say top and bottom. So my derivative, so I could do, I'll try and do it the way you guys like. So it's the bottom times the derivative of the top, or the derivative of the top times the bottom. Same thing. So the derivative of the top, and if you like, you can even just write literally the derivative of the top, meaning you can write, oh, it's the derivative of x to the fourth plus cosine x, and save that differentiating for the next step. You do have to actually take that derivative at some point, but you can write it this way first if you want to. So it's the derivative of the top times the bottom left alone minus, switch it up, right? I did the derivative of the top, now I have to do the derivative of the bottom times the top left alone. I guess I should do it so, right? It's f, it's the derivative of the top. Right? It's so hard for me to do it this other way. I'm like, bottom, derivative of the top minus top times the derivative of the bottom, which is the derivative of e to the x plus 2 sine x. All over the denominator squared. Now, I don't recommend doing this if you don't have to. Right? Like if you can just find the derivatives of each thing, you should do it that way, because this is a lot of extra writing, because now I'm going to go rewrite the whole thing again and actually take this derivative. I'm going to make a mistake, and then I'm going to point it out. So here's the mistake I'm going to make. I'm going to write this. So the derivative of x to the fourth plus cosine x is 4x cubed plus negative sine x or minus sine x times this, and then minus x to the fourth plus cosine x times the derivative of e to the x plus 2 sine x, which is e to the x plus 2 cosine of x, all over this thing squared. And the mistake I'm making here is not using any parentheses, right? If you write it like this, someone might know what you mean. This looks a little wonky here. They might know that you mean all of this times all of this, but what you've really written is 4x cubed minus sine x times e to the x plus 2 sine x minus x to the fourth plus cosine x times e to the x plus 2 cosine x. We really, really need these parentheses. Like, they are vital here. So I need all of this times all of this. And I need minus all of this times all of this. It's really, really important for the quotient rule especially. If your numerator or your denominator have more than just one thing added or subtracted together, you really need parentheses around that, because all of that has to be getting multiplied by the derivative of the other part and vice versa. So err on the side of too many parentheses when you're using the quotient rule, because you need them. Okay. Sure. So, yeah, okay. Let's see.
We're going to leave that as is, or are we going to simplify it?
I'm definitely going to leave that as is. That's a good question, though. So hopefully no one asks you to simplify this. But, I mean, so we could simplify it. It's not nice, right? So if we had to simplify, it's... The thing I want to say here is there's not a lot to be gained by simplifying this. All you really get to do is you get to multiply off the top, and I would leave the bottom as it. So if I was simplifying this, it would be ugly. It'd be 4x cubed times e to the x. It'd be 4x cubed times 2 sine x, which would be, I guess, 8x cubed sine x minus sine x e to the x. Minus sine times 2 sine is minus 2 sine squared x. And then I can do the same thing here. I get, let's see, minus x. So here I have to also remember the minus sign distributes. So it's minus x to the fourth e to the x. Ugh. Minus x to the fourth times 2 cosine x minus cosine x times e to the x minus cosine x times 2 cosine x, which is minus 2 cosine squared x, all over the same denominator. No one should ever ask you to do this. The one thing I will say is if someone did ask you to do this and did ask you to simplify, there is one thing you can actually do here that they would probably, there is one not good reason they can ask you to do this. And the reason is that if you put negative 2 sine squared x minus 2 cosine squared x together, that ends up equaling minus 2. Because you get minus 2 times the quantity sine squared x plus cosine squared x. But no one in their right mind is asking you to simplify this, because it's just, there's nothing to be learned from that. The reason we are usually simplifying derivatives is because we're often trying to see where they're equal to 0. And so we're like, oh, I'm going to take this derivative, find the critical point, which we probably haven't talked about yet, but that's where we're going to, and maybe try and graph the thing. In this case, solving this equal to 0 is probably close to impossible, if not very, very hard. So yeah, usually these problems are like, don't simplify, just do it. And then leave
Really
it.
quick. I know we're not going to use the chain rule, but if you would you take the denominator and put that to the negative first power? And
Yeah.
Okay.
So if you were going to try your hardest to avoid using the quotient rule ever in life, you definitely write this as x to the fourth plus cosine of x times e to the x plus 2 sine of x to the negative 1. So then you have to use the product rule and the chain rule. So you do the derivative of this times this left alone plus this left alone times the derivative of this, which is going to require the chain rule. Yeah. And then, so you can always avoid the quotient rule if you want to rewrite every fraction as the top times the bottom part, all in parentheses to the negative first power.
Mm-hmm.
Yeah. So I think I think it makes sense to finish the trig derivatives and then take a break. So when I say finish the trig derivatives, I mean we know that the derivative of sine is cosine. And we know that the derivative of cosine is negative sine. And before we move on, I really want to ask or make sure that everyone is cool with this, that everyone is okay. If anyone would like me to explain either one of these again, graph them, or do the limit definition. I know we did the limit definition of the derivative for sine. I could do it for cosine if anyone wants to see that. And you can either say words, message me in the chat, message me privately in the chat if you want me to say anything more about that before we talk about the rest of the trigonometric function derivatives. I'll give you a moment. All right. Seeing that no one has requested more information on the derivative of sine and the derivative of cosine, we'll move on to the other four functions: tangent, cotangent, secant, and cosecant. And I'll remind you that each of tangent, cotangent, secant, and cosecant are just a quotient of the other trig functions. Specifically, let's start with tangent. Let's start with tangent on the other side, because I'm going to leave this side so we can write all 6 trig functions in the usual order and pattern of writing them. I know I said this about the product rule. I will say the quotient rule is a rule you should memorize, right? It is definitely product rule, quotient rule, power rule, and a chain rule eventually. Those are all rules you be like, I know those up, backwards, forwards, up, down, left, right. So let's find the derivative of tangent of x, which we are definitely going to write using the derivative of the quotient sine of x over cosine of x. Yes, it is certainly possible to take the derivative of tangent using the limit definition. You'd have to use the funky angle sum formula for tangent. We don't want to do that. We want to use the knowledge we already have to help us make it easier for the rest of the things. So, just like before, we're going to find the derivative of the quotient by using the quotient rule. So I'll do it the way you guys like. So it's the derivative of the top. So it's the derivative of sine, which is cosine, times the bottom. Right? And if you like, you can even label things. I can call this F, I can call this G. I can say it's F prime times G minus the top times the derivative of the bottom. The derivative of cosine is negative sine. So I've got my F G prime all over the denominator squared, which is cosine of x over g squared. All right, well, let's see what I've got. I've got cosine x times cosine x is cosine squared x. Sine x times negative, so negative sine x times negative sine x is plus sine squared of x, all over cosine squared of x. And the easiest way to simplify this is to see that cosine squared x plus sine squared x is the trig identity and it's equal to 1. So I end up with 1 over cosine squared x. And we never write it that way. We always write it as, well, 1 over cosine is secant. So 1 over cosine squared is secant squared. So this is secant squared of x. And this is definitely one you're going to want to memorize all 6 trig derivatives for sure. So I'm going to write that on the other side so we can have it there. So the derivative of tangent is secant squared x. don't have to write parentheses around your arguments, but I would too. So we've got the primary trig functions. Now we want to find the derivatives of the reciprocal trig functions. And we're going to do cotangent next. So cotangent works out very, very, very much the same way as tangent. So I hate to erase all this work so quickly, but I'm going to. I'm going to cheat a little bit, leave myself some of the stuff up. So tangent's going to take a cotangent just the same amount. Oh, I should have done that. There's something cool I could have done. Oh well. We'll get there. I can still do the cool thing I want to do. So let's do cotangent. Derivative cotangent of x. Well, just like tangent is sine over cosine, cotangent is cosine over sine. And so just like before, I'm going to use the quotient rule again. Derivative cosine is negative sine times sine minus the top, which is cosine, all over the derivative of the bottom, which is cosine. All over the bottom squared, which is sine squared of x. So let's see, on top I have negative sine squared x minus cosine squared x, all over sine squared x. All right, anybody help me out? Can anybody tell me what negative sine squared x minus cosine squared x is equal to?
-1.
Yeah, and you can either just say, or you can factor out the -1. Say, oh yeah, it's -1 times sine squared plus cosine. So you get -1 over sine squared of x. 1 over sine of x is cosecant of x. So 1 over sine squared is it's cosecant squared. So we get negative cosecant squared. And I'm going to write that one. So typically, when we're writing out all the derivatives of the trig functions, we usually write them in this order. We usually write it as sine, cosine, tangent. And the reason I think we picked this order is because sine divided by cosine is equal to tangent. So it's kind of a nice visual reminder of the division there. And then to the right of each of these primary trig functions, we write their reciprocals. So the reciprocal of tangent is cotangent. So the derivative of cotangent of x is equal to negative cosecant squared of x. And we're going to do the same for sine. So the reciprocal of sine is cosecant, which we haven't found yet. The reciprocal of cosine is secant, which we also haven't found yet. But we'll do those two right now. I'll say 1 or 2 words and then take a break. Yeah, I'm fine. I'm done. Let's do the derivative of secant. Secant is actually even easier than tangent and cotangent, because secant of x, how do you write secant as a fraction or a quotient? Secant's 1 over cosine. Oh, yeah, there's some, sorry. Let me, I'm going to some notes here. Yeah. Don't worry about that in there. That's for me for later. So using the quotient rule here, it's the, I really want to say it's the bottom times the derivative of the top. I guess I'll say it's the derivative of the top times the bottom. What's the derivative of the top?
0.
Times the bottom. It doesn't really matter what the bottom is, but it's cosine. Minus the top times the derivative of the bottom, which is negative sine, all over the denominator squared, which is cosine squared. 0 minus a minus is plus, so I get plus sine of x, all over cosine squared of x. But nobody ever leaves the answer this way. So it is correct that the derivative of secant is sine x over cosine squared x. But the way people write the answer is the following way. They break up sine x over cosine squared x as 1 over cosine x times sine x over cosine x. And then they rewrite that as, well, 1 over cosine is secant of x, and sine x over cosine x is tangent of x. So the derivative of secant x is secant x tangent x. I want to point out that this derivative and the next one are kind of unique in that most of the time when you take a derivative of some function of x, where it's kind of like a simple function of x, like e to the x or natural log of x, which we haven't done yet, or sine or cosine or whatever, like most times you take the derivative of some basic function of x, you only get one function of x back. But here, we kind of get two occurrences of x. Like, there's not really a way that we have of writing this result as just one thing of x. It is secant of x times tangent of x. It is two functions of x multiplied together. And that is, it's a little bit unique. There are not a lot of other regular basic functions where the derivative has two occurrences of the variable you're talking about. Oops, that's not the right color pen. I mean, it doesn't really matter, but it's nice to use the same colors. That's going to be secant x tangent x. And now I'm going to make an observation that I think is worthwhile. And this has to do with the way we name trig functions. There are three trig functions and there are three co-functions. The functions I'm thinking of, the regular, there's not a good name for like the not co-functions, but the not co-functions are sine, tangent, and secant, because they don't start with a co. The co-functions are cosine, cosecant, and cotangent. And there are lots of rules about how co-functions work. So tangent and cotangent are co-functions. Sine and cosine are co-functions. Secant and cosecant are co-functions. The most notable thing I think is that if you take co-functions of complementary angles, you get the same result. Like sine of 30 degrees is equal to cosine of 60 degrees. Or tangent of 82 degrees is equal to cotangent of 8 degrees, which is not something you can calculate, but it's true. The reason I mention this is because there's kind of an interesting correspondence between the functions and their co-functions. And again, the naming is important. Tangent and cotangent are co-functions. Sine and cosine are co-functions. Secant and cosecant are co-functions. Take one of the regular three functions, like sine. The derivative of sine is cosine. The derivative of cosine, this one's kind of one where it doesn't work as nicely as the other ones, but you can basically think of the co as turning on or off the function. So like the derivative of cosine is cosine, which is just sine, but it's negative. That one is, okay, the next ones are better, trust me. The derivative of tangent is secant squared. Slap a co on all of it. The derivative of cotangent is cosecant squared with a negative. Derivative of secant is secant times tangent. We're going to do it, but I'm going to tell you the derivative of cosecant is cosecant. Wow, maybe I could write that not terribly. Right, derivative of secant is secant tangent. Derivative of cosecant is cosecant cotangent with a negative. And we're going to do it right now. But I really want to tell you, I often just remember, I just remember these ones. And by I can't, yeah, like I don't really remember these two derivatives. What I remember is the derivative of tangent is secant squared, and then if I put a co on it, I get the derivative of cotangent is cosecant squared with a minus sign. Similarly, I remember the derivative of secant is secant times tangent, and then the derivative of cosecant is cosecant times cotangent with a negative sign. That's really how I remember these. Maybe not at this point since I've done them so many times, but like in the beginning, I didn't want to memorize 6 things. I only want to memorize 4 things, and the other 2 just kind of came along for free. So let's do the derivative of cosecant real quick, and we'll say a couple other things. So the derivative of cosecant of x, we are expecting it to be negative cosecant x times cotangent x. And it's going to be. It's going to be the derivative of 1 over sine of x. And the derivative of 1 over sine is the bottom times the derivative of the top, which is 0, minus the top, which is 1, times the derivative of the bottom, which is cosine, all over the bottom square, which is sine squared of x, which ends up being negative cosine of x, or sine squared of x, which later on, when you see this in Calc 2, or 21B, I should say, you're like, how do you integrate that? You rewrite it. You rewrite this as negative 1 over sine of x times cosine x over sine of x. And then you're like, hey, that's just negative cosecant of x times cotangent of x, which I recognize as the derivative of cosecant, so its antiderivative is, which I know we're not to antiderivatives yet, but I will warn you, this definitely comes up. It's like, how do you integrate that in 21B? By rewriting it as something we know it's the derivative of. So yeah, it is what we said it is. All right, 2 things before we take break. Thing 1, when you're talking about trig functions, every cofunction has a derivative that's negative. Cosine, derivative is negative sine. Cotangent, derivative is negative cosecant squared. Cosecant, derivative is negative cosecant cotangent. So each cofunction is always having a negative sign in front of their derivative, assuming it's not more complicated than just the regular function. Whereas the not cofunctions, again, there's no good name for them. The other trig functions, the ones we like better, I guess, sine, tangent, and secant, they all have positive derivatives. There's a thing there. No, there's a thing in 21. So you'll see in 21B that we definitely use sine and secant and tangent a lot more than we use cosecant and cotangent because their derivatives are positive. And there's a specific thing I'm referring to that you don't know about. There's a specific thing that I'm referring to that you don't know about yet. Sorry, one sec. Called trig substitution, where you could choose either one, but we choose the one where the derivatives are positive. The other thing, which is something a student showed me when they were thinking about this stuff, and I just think it's kind of worthwhile, is they said this is how they remember the derivatives of secant and cosecant and tangent and cotangent. I am okay mostly, but I am going to check with my wife. Thank you for asking. I'm all right, but well, yeah, I'm mostly all right. So the other thing was that they did this, which I thought was pretty clever. They actually they were this way. They start with tangent. So they did this for the derivatives of tangent and secant. They said that the derivative of tangent is secant x times secant x. The derivative of secant is secant x times tangent x. And then they did a similar thing for cotangent. They said for cotangent, the derivative of they did negative cosecant here, cosecant here. So derivative of cotangent is negative cosecant times cosecant. Derivative of cosecant is negative cosecant times cotangent. Well, it's kind of neat. I don't think there's a good one for sine and cosine. So yeah. Maybe there is. I don't know if there is one. So yeah. All right. Let's take a 10-minute. Let's take a break till 10 minutes. Let's take a break till 3:20. I'm going to say. Maybe I'll come back a little sooner than that, but you can definitely break till 3:20, and yeah, I will be back at 3:20. I will turn off the mic. Leave my video on. So definitely, I will say, you definitely want to memorize these. I have told students in the past, write them all down, take a picture of them, make the background of your phone, just so that you can see them all the time and really just make them part of your soul and memorize them. Maybe not part of your soul, but you get the idea. So trig derivatives. You definitely want to memorize these, just like you want to memorize the product rule, memorize the quotient rule, memorize the power rule, memorize the derivative of e to the x, eventually the derivative of the natural log of x once we talk about it. And yeah, so we could definitely do more examples with our new host of derivatives. In fact, here's what I'm going to say really is that, so I have a handout. Let me see where I put it. Just one sec. I should have done this a moment ago, but I forgot to. Canvas. Let me share my screen so you guys can see this. I'm pretty sure this is on Canvas. Take a look at Canvas for a second here, the Co-21A class. And if it's not here, I will find it. Let's look at modules. Let's go down. Is it not here, really, James? I guess it's not. So there's a handout I'm going to post. Let me just find it for you guys so I can open it up just because you should see this. I think it's worth your while. Co-21A handouts. Yeah. Really? Well, I thought I had a handout. Maybe it's a worksheet, not a handout. Yeah, there we go. So I have this derivative worksheet. I will post those up for you guys. I think this is there's a lot of derivatives on here, as you can see. A lot of them requiring either the product rule, the power rule, the quotient rule, the chain rule, trig function derivatives, or some combination of those. And I also have solutions, or at least answers, right? So if you want to, in fact, I don't have the actual original file. Here's the answers, which I'll also post up. So there's more answers. It's more answers, not solutions. As you can see, none of my answers are simplified, which is also what I would expect from you. Now, what I want to say is I will post both of these up. I think these are definitely good practice, right? Where you can just be like, I'm going to do a bunch of derivatives just to get good at finding derivatives. So I will post these today after class, after I email my doctor. And I will encourage you all, not require you, of course, but definitely encourage all of you to work on those if you have the wherewithal to do so. I think, again, I know you have lots of other work to do. So if you find yourself wanting more practice and needing more practice, those are good problems that you will also be able to see the answers to. And the answers written in a way where they're unsimplified, so you can definitely see that if you've done the derivative first step correctly, you would be right. And then if you wanted to do more simplification, you could, but you shouldn't. So yeah, I'll get those posted later. That said, I think our time would be spent better by moving on to talking about the chain rule and how we can use it. So let's talk about the chain rule because that's where we're going next. So where we're going to go is chain rule, I guess then implicit differentiation. And we might have time. So chain rule. So chain rule, there's sometimes people talk about like the power rule version of the chain rule. There's one chain rule. There are way different ways of thinking of it, but the chain rule is a chain rule. So I'm going to start here. I'm going to start with the repeated product rule, which is really just a chain rule. I know I talked about this last class where I said if you have like a triple product, you get the derivative of each part times the other not derivative parts. So I'm just going to remind you, because we definitely talked about this last time, that if I take the derivative of f of x times g of x times h of x, you're going to get three pieces added together. And each of those pieces, or summands, right? When you sum things, each of the things added is a summand. Each of the summands is one derivative times the other two not derivatives. And you have to get each derivative showing up in one spot. So the derivative of this is f prime of x times g of x times h of x, plus, then we do it again, but instead of having f prime, we have to have one of the other functions derivative, f of x times g prime of x times h of x. And then, sorry, that's not an h prime, that's just an h, it's just a stray mark there. And then finally, the last one is f of x times g of x times h prime of x. So that again, right, if you're taking the derivative of a product of 1, 2, 3 things, you're going to get 1, 2, 3 pieces added together, and each piece is going to have one derivative and two not derivatives. And you have to have each of the different functions derivatives showing up exactly once. And you can do this for a product of any number of things. So you take the derivative of f of x times g of x times h of x times j of x, which I'm not going to write the of x's because it's not really necessary. And I know that the derivative of this would have 4 pieces added together. And each piece would have 1 derivative and 3 not derivatives. 1 derivative and 3 not, 1 derivative and 3 not, right? Each derivative showing up once. So the derivative of this product of 4 things would be f prime times g times h times j plus f times g prime times h times j plus f times g times h prime times j plus f times g times h times j prime. And so on. And you might be wondering, James, what's the point? There's a point. The point is, I'm going to use this to show the product, to show the, well, yeah, the product rule, which is really just the chain rule hiding out, kind of like how exponentiation is just repeated multiplication. I'm going to use this to find the derivative of the following. The derivative of f of x to the nth power. Now, before I do that, I should point out, most of you might know what to expect, but let's actually, before we do this kind of generic, not specific example, let's actually do a specific example. So we're going to come back to this, but let's take a look for a second. Let's say, I want to take the derivative of, and let's not make it too crazy. Let's make it x cubed plus 1 to the second power. Now, here's what I'm going to do. I'm going to multiply it out because I made the power small enough that I can multiply it out, right? Hopefully, we're all cool with how to multiply out x cubed plus 1. This is the derivative of, so x cubed plus 1 times x cubed plus 1 is x to the 6th plus 1x cubed plus 1x cubed is 2x cubed. And 1 times 1 is 1. And now let's take the derivative. The derivative is going to be 6x to the 5th plus 6x squared plus 0, which I'm not going to write. What can I factor out? Well, I don't actually want to factor out all of them I can factor out. I could factor out a 6x squared. But I'm going to, well, and actually I will. I'm going to write it in kind of a funky way. I'm going to write this as 6x squared times x cubed plus, sorry, I'm making a dumb mistake somehow. No, 6. Did I make a dumb mistake here? No. Sorry, brain work plus 1. Yeah, okay, yeah. Sorry. But then I'm actually going to rewrite this as 2 times x cubed plus 1 to the first, x is the first power there, times the 3x squared that's left here. And here's what I want to point out, which is hopefully not too surprising. That if I take the derivative of some stuff squared, I'm really going to think about using the power rule on that stuff. The derivative of x squared is 2x. The derivative of some stuff squared is 2 times your stuff. But you have to multiply by the derivative of the stuff. That's the idea of the chain rule, really, is that when you're taking the derivative of some composition of functions, you do the derivative of the outer function. Here, the outer function is you got something squared. So you do the derivative of that, and you leave the inside something alone. So the derivative of some stuff squared is 2 times your stuff left alone to the first power. But then you have to multiply by the derivative of the inside function, which in this case is 3x squared. That is the whole idea behind the chain rule. And we can see it here through repeated multiplication. So the derivative of f of x, again, I'm going to drop the x just to make it easier to write out. This is the derivative of just f to the nth power. Well, I know what f to the nth power is. It's f times f times f times f times f times f n times. So this is the derivative of f times f times f times f. How many times? N times. All right, but I already spent just a couple minutes before on the other side of the board talking about how if you take a derivative of a product of many things, you get that many pieces added together, right? Derivative of a product of 3 things, you get 3 pieces added together. Derivative of a product of 4 things, you get 4 pieces added together. Derivative of a product of n things, you're going to get n pieces added together. And each of the pieces is going to have one function derivative and the rest of them not derivatives. So here's how this is going to look. I got f times f times f times f n times. So I'm going to have in the first piece f prime times the rest f's. And the second piece, I would normally write the f primes down front, but I could write, okay, I've got an f times an f prime times the rest f's. And I should be a little more careful, right? The way I'm writing this here is here there are n minus 1 f's over there. Right here there are n minus 2 of them, right? Because there's n things in each of these. One thing here, n minus 1 things there. One thing here, one thing there, and then n minus 2 there. And then similarly, you could have, you know, f times f prime times the rest f's. And there would be, n minus 3 of them there. And so on, all the way to the very last term, which would be f times all the way, right? N minus 1 of those. And the very last one would be f prime. But here's what you really want to see. Each of these things is the same. Each of these things is f prime times n minus 1 f's, which you could totally write f times f n minus 1 times as f to the n minus 1 power. I should not write parentheses around it. When you write parentheses around the power like that, you actually mean that derivative. So that is poor notation there, which is too bad because I would like to use it, but yeah. Yeah, if you write a function with parentheses around the superscript like that, you actually mean take that derivative. So if someone writes this, they mean the 6th derivative of f. If someone writes this, they mean the 6th power of f. So this is going to equal, so this is f prime times f to the n minus 1 power. This is f prime times f to the n minus 1 power. And each of them are the same thing. They're all f prime times f to the n minus 1 power. And there's how many of them? So here's the thing, right? This, and all these things are all the same. And there are n of them, right? Because we said there had to be n pieces. So this is really n times f prime times f to the n minus 1. Whereas I'm going to rewrite it so it's a little more explicit. This is n times f of x to the n minus 1 power times f prime of x. Stop, take a second to think about what we've got. We took the derivative of some function to the nth power, or some stuff to the nth power, and our derivative was the derivative of something to the n, right? N times something to the n minus 1, but then we had to multiply by the derivative of the insides. That's the chain rule. It's not the only way the chain rule, I mean, that's the general idea of the chain rule, is that you differentiate the outside function, and then you leave the insides alone, and you multiply with the derivative of the insides. The only thing that gets more complicated is your outer function isn't always just some power of your inner function. It could be sine of your function, or e to the your function, or anything can be the outer function. It doesn't have to be raised to a power. But we start with raised to a power because it's kind of easy to do this. So that said, we could ask something like, what's the derivative of 2 sine of x plus x to the 6th to the 98th power. And although it looks kind of like a pain, you could, I suppose, if you wanted to make your life a living hell, multiply this out. You definitely shouldn't, right? It'd take probably take me a good, I don't know, take a long time to write that all out. I don't know how long. That's not the point, right? The point is, I've got some stuff to a power. I know the derivative of x to the 98th power is 98 times x to the 97th. So I know the derivative of some stuff to the 98th power is going to equal that same, or I should say 98 times that same stuff to the 97th power. But then we have to multiply by the derivative of that stuff. So my stuff stays the same, right? That's just going to be 2 sine of x plus x to the 6th times the derivative of that stuff, which is 2 cosine of x plus 6x to the 5th. That's it. That's my answer. And you definitely, there's no good simplifying to do here, right? There's no multiplying this out. There's no combining these together. We just leave it as is. And that's kind of the gist of the chain rule. I know I've said that a few times, but it really is. So if you have a function, if you've got some garbage like, I don't know, 4x to the 5th minus 3 tangent of x to the 8th power, you could multiply that out. I've definitely seen people multiply it out on tests, which I was not pleased about. That's why I make my powers really big on tests if I'm writing a test. But this one, we're going to be okay. I've got a thing to the 8th power. The derivative is 8 times that thing to the 7th power times the derivative of that thing. The thing is 4x to the 5th minus 3 tangent x. I want to be very, very emphatic. When you take the derivative of the outside part, you have to leave the inside part unchanged. Too many times I've seen people write 20x to the 4th minus 3 secant squared right here because they did the derivative of the outer function and they put the derivative of the inside function inside there. We have to leave it alone. In fact, I should get to the point and say the actual formula for the chain rule. But I'm going to multiply by the derivative of this, which is 20x to the 4th minus 3 secant squared x. Okay, so chain rule for real. So people often call this the power rule version of the chain rule, or the chain rule version. It's the one rule version of the other rule, either chain rule version of the power rule or power rule version of the chain rule. I don't think you should memorize this specifically, although you certainly should be aware of how to do it. What we really want to know is the chain rule for real. So the chain rule for real says, well, your outer function doesn't have to be some power. Your outer function can be anything. So the chain rule says, if I'm going to take the derivative of a composition of functions, typically I like to write it as f of g of x, although you will certainly find people who write it, in my opinion, the less nice way. The derivative of f composed with g of x. These both mean the same thing. I just think this is much more explicit about what's going on. Well, just like in the previous problems, we take the derivative of the outer function, we leave the inside function alone, and then we multiply by the derivative of the inside function, which leaves us with f prime of the inside function left alone, so just good old g of x, times the derivative of the inside function, which is g prime of x. That's your chain rule right there. And really, it's the same here. I guess you could try to I hate to write this next way, but I will write it for those of you that prefer this notation, which I hope is none of you. But if it is, that's fine. No judgment, small judgment. No judgment, small judgment. You can write this as f prime composed with g of x times g prime of x. That's how you could write it using this notation. That seems really kind of weird to me, but whatever. All right, so what this means is you could take the derivative of something not too terrible, like sine of 2x cubed plus 1. And say, okay, the derivative of sine of some stuff, sine being my outer function. Well, the derivative of sine of x is cosine of x. So I often think about what the plane derivative is, like the function where the insides are just x. And then I replace that x with stuff. So I'm like, okay, the derivative of sine of x is just cosine of x. The derivative of sine of stuff is cosine of that stuff times the derivative of that stuff. So if you're saying stuff instead of x, you should always be saying, oh, I have to multiply by the derivative of that stuff. Really, you have to do it for x as well. Technically, I'm using the chain rule every time I take a derivative. The derivative of sine of x is take the derivative of the outside function, it's cosine of my stuff, times the derivative of my stuff, which is, hey, that's 1. So if your inside part is just x, you use the chain rule every time you just multiply by the derivative of the inside, which is 1. Okay, so here it's going to be cosine of the derivative of 2x, or sorry. So let me show you a mistake. I almost did this. That's not right. Right, it's the derivative of the outside, leave the inside alone, right? F prime of g, not f prime of g prime. That's what I've written there. If you're thinking of this as f and this is g. It's f prime of g times g prime, which is 6x squared. And you wouldn't need a parentheses around 6x squared because it's just kind of one term, nothing added to it, but I still have parentheses. So let me give you a visual. So we're not going to prove the chain rule. I'm not going to prove the chain rule. It's a little complicated. But I am going to give you a function or an example of a function where, what's the word I'm looking for? That makes it maybe somewhat obvious that, oh yeah, this is really actually what's supposed to happen. And I'm going to do it that way. So let us look at the function sine of 2x. And I'm also going to look at sine of x just because. And I'm going to graph things. And we know already the derivative of sine is cosine. And so I'm going to do this graphing of derivatives thing. So I think we did last class, but maybe I'm thinking of my 17A class. So I'm going to draw sine of x first. So there's 2 pi. Let me look at this a little more. So there's cut it in half, half, 1. Okay, so sine of x looks like it usually does. It starts at 0 and then 1 and then 0 and then negative 1 and then 0 as we go through the various quadrants. So that looks not as good as it should. Okay. And then sure. All right. And we can graph its derivative. Now we know its derivative is cosine, but we can also graph it by kind of thinking about the slopes of the tangent lines. So, and I honestly don't remember if we did this last class or not. I know I did it in my 17A class. I'm not sure if I did it here for you guys or not. If I didn't, well, now I'm doing it. So let's graph the derivative. So at this point here, the tangent line is horizontal, slope of the horizontal line is 0. So the derivative is going to be 0. Same thing here. So pi over 2 and 3 pi over 2, we can see that the derivative is 0. And again, this is y equal to sine of x. Bear with me. This definitely is worthwhile, I think. Here, well, we know that cosine of 0 is 1. And that tangent line definitely looks like it would have a slope of 1 if we drew the tangent line there. So yeah, we're going to go with a 1. Okay. So, right, a 1. And then it definitely looks like here the slope is negative 1. And then back here it looks like the slope, well, I didn't drop that great, but it looks like the slope is 1. So great, there's the derivative of sine. And it definitely is cosine And it looks like cosine. It looks kind of like cosine, I'm not gonna lie. Okay, but now here's what I really, really wanted to show you. Sine of 2x is the sine function, except it has been horizontally compressed. Right? The period for sine of 2x isn't 2 pi, it's 2 pi divided by 2, which is pi. So from 0 to pi, we get the whole, middle, top, middle, bottom, top. So we're going to break this up into 4 equal sections, so half and then half and half. So pi over 4 is where I top out. Pi over 2 is where I'm back at 0. So I started at 0. Pi over 2 is where I'm back at 0. 3 pi over 4 is where I'm going to go down to -1. And pi is where I'm going to get back to 0. So it's going to look like this. And then it would repeat itself, right? It would do the same thing again. And hopefully you guys can see this already, because it's kind of important to be able to see the thing I'm drawing here. I mean, maybe I'll also, maybe. I might also show this. Here's what I want to point out. And actually, no, yeah. So if I look here at pi over 4, that's where it tops out, that's where the tangent line is horizontal. So at pi over 4, the derivative is 0. And at 3 pi over 4, the derivative is also 0 because it bottoms out and the horizontal tangent has a slope of 0. And then, and here's where things are different. At the origin, the green function has a slope of 1. The red function is steeper because we have to have more vertical travel in a compressed horizontal distance. That's a lot steeper. It's like twice as steep. It's like the derivative there is 2 instead of 1. And similarly, at pi over 2, it's steeper than it is over here at pi, the green function. It's like -2, which would be over here at pi over 2. And then back at pi, it's steep again, like +2. So look at what I've got. And I don't think I made my y scale quite as big as my x scale here. Look down there, sure. It looks a lot like this. Which definitely looks like cosine, but it looks like cosine has been scrunched horizontally, so it also has a period of pi, which means it looks like I'm looking at cosine of 2x, because that would be a cosine function with a period of just pi instead of 2 pi. But it also looks like I've vertically stretched it to have an amplitude of 2 instead of 1. But look, really look. If I'm thinking about the chain rule, the derivative of sine of some stuff should be cosine of that stuff times the derivative of that stuff. Oh, that works. So this is a visual example I think is nice to see that, oh yeah, if you take the derivative of sine of 2x, you really do get 2 cosine of 2x. So there's kind of an example of, oh yeah, here's the chain rule really kind of working. All right, so let's look at some examples now. So let's say we had something like f of x equal to, I don't know, tangent of 3x squared plus 5x to the 7th. I want to take the derivative of that. So my outer function is tangent of some stuff. The derivative is, what's the derivative of tangent of x? Secant squared of x. So the derivative of tangent of some stuff is secant squared of that stuff times the derivative of that stuff. So it's secant squared of, that goes right there. And then, I wish there was like a good, I guess I could say like derivative goes right there. So it's secant squared of 3x squared plus 5x to the 7th times the derivative of that stuff, which is 6x plus 35x to the 6th. Or I can say my function is g of x equal to cosecant of x squared plus e to the x. And this is where the cosecant and the secant ones are a little extra tricky. So the derivative of cosecant of x is negative cosecant of x cotangent of x. I should really emphasize it is negative cosecant of x times cotangent of x. It's not cosecant cotangent of x. It is cosecant of the thing times cotangent of the thing with a negative in front. Sometimes I accidentally leave off the negative. There's a negative. So here's what I really want to make clear. The derivative of cosecant of some stuff is negative cosecant of that stuff times cotangent of that stuff. The stuff appears twice in the cosecant function and the cotangent function. So it's negative cosecant of x squared plus e to the x times cotangent of x squared plus e to the x times what? The derivative of the stuff, which is 2x plus e to the x. You don't get the derivative of the stuff twice, right? The chain rule is still just take the derivative of the outer function. The outer function was cosecant. The derivative is cosecant of thing times cotangent of thing, or the thing is x squared plus e to the x, but then you multiply by the derivative of that just once, 2x plus e to the x. Same is true if you have secant, right? If your function was f of x equal to secant of something funky, like secant of, I can make it tricky. I'm gonna make it tricky. X cubed times e to the x. Oh, I'm gonna use the product rule. Then the derivative secant of that thing is secant of thing times tangent of thing times derivative of thing. So it's secant of x cubed e to the x times tangent of x cubed e to the x times the derivative of x cubed e to the x. And notice I didn't actually write the derivative there. I wrote just take the derivative of that. If you do that, you actually have to then write what the derivative is. So you can either erase it and write the derivative, or you can write a whole new step. I'm gonna write a whole new step just because I don't know. That's probably what most people will do. So it's secant of x cubed e to the x times tangent of x cubed e to the x times the derivative of x cubed e to the x, which does require the product rule. So the derivative of x cubed e to the x is the derivative of x cubed times e to the x plus x cubed times the derivative of e to the x, which is e to the x. Okay. They do get more complicated, I'm not gonna lie. I definitely encourage everyone to take a look at the thing I will post right after class, which is the, I think I call it like the derivative worksheet. And then I will also post right under it the solutions to it. But I really encourage you all, if you have the time, if you want the practice, to try and do the problems without looking at the answers until after you feel like, okay, I did this one right. And then take a look, right? Really make yourself try to do the problems without looking at the answers, because that's really the way you're going to get better at this stuff. Faster at it, right? Sometimes speed is important. You have to be able to do these things quickly because you only have so much time for your tests, depending on who's giving you your test. But I want to get one more because this kind of problem comes up a lot. Let's say I want to take the derivative of, let's say, cotangent to the 6th power of x to the 7th plus sine of, I'll just make it sine of x for now. All right. So I have to ask everyone, what's my outermost function? Is it cotangent of a thing, or is it being raised to the 6th power of a thing? This is most easily seen if we rewrite this in the less abbreviated way. So whenever I'm taking the derivative of trig function to a power of some stuff, I'm almost always going to rewrite it as still the derivative, right? I'm not taking the derivative yet. I'm just rewriting this, of cotangent of my stuff to the 6th power. And then it's probably easier to see that the outermost function is being raised to the 6th power. So when I take the derivative here, I'm going to say, oh, I've got some stuff to the 6th power. The derivative of that is 6 times my stuff to the 5th power times the derivative of that stuff. And now here's where you guys might not be so thrilled. Have to use the chain rule again. If I take the derivative of this stuff, this is still a composition of functions. This is cotangent of some new stuff. So if I say, okay, well, that's going to be 6 times cotangent of x to the 7 plus sine of x to the 5th times, now I'm taking the derivative of cotangent of some new thing. And the derivative of cotangent of some new thing is negative cosecant squared of new thing times derivative of new thing. So new thing is x to the 7 plus sine of x. And the derivative of new thing doesn't require the chain rule because it's just nice, easy functions of x. The derivative of x to the 7th is 7x to the 6th. The derivative of sine of x is cosine of x. And that would be our final answer.